Okay guys, so we're going to do a problem today. You have seen this one many times, so I always try to kind of follow this procedure when I solve every single problem. So this is the problem over here, problem number 10. So first thing I do is always read carefully the problem and do a summary. So it will be water contained in a rigid cylinder. So this is very important over here. So I do the rigid cylinder, which tells me what? That we are dealing with a closed system. And you know that is water. It's initially in saturated vapor state. So you can say state 1 will be saturated vapor with P, so P1 equals to 4 bar. The water is heated, so that means we're gonna have heat over here until the temperature is 400 degrees Celsius. So let's say state 1, heat, until state 2, where the temperature is 400 degrees Celsius. Determine the heat transfer in kilojoules per kilogram, ignoring kinetic and potential energy. Okay, so I'm going to add over here, ignore kinetic and potential energy. All right. So like I said before, in this type of problems, either the PV or the TV figures are crucial. So I'm just gonna randomly select over here the PV. Okay, so what do we know initially? We know initially saturated vapor. So if you remember, this point over here is the critical point, and on the right hand side will be the saturated vapor. This side will be the saturated liquid. So we know we are along this line. So this will be, let's say, 1. Okay? And we know in this type of figure, what we're going to have is lines of constant temperature. So certain temperature is going to go through this line over here. All right. So the first thing we can do is actually find out what is the temperature. So in order to do that, what do we know? We know that P1 equals 4 bars, which is 400 kilopascals. And we deal, and we know we are here at saturated vapor state. All right, so we need to go to those tables. So we know it's water. So let's see. Table A4 is for water, but this is saturated water. It will be whatever happens over here. So we could maybe use that one, but let's see what we have on the other tables. Okay, table A5 over here. If you look at it, gives you the pressure. So let me try to approach this to the scan, otherwise go to table A5 in your textbook, and we look at 400 and 400, and if you can read the temperature at the top says 143.61. So we can see over here from table A5 at P equals 400 kilopascals, we know that the saturation temperature, which will be equal to T1 in our case, is equal to 143.61 degrees Celsius. So go to the table and check that value. So really this line over here is T1 equal to 143.61 degrees Celsius. So now we apply heat. So we know we're going to go to another line which is going to be a much higher temperature. So this figure is not to scale, but so we know T2 here will be 400 degrees Celsius. Okay, so another thing we can see over here from this problem is that we know that this will be V sub 1 over here. Okay, so V sub 1 we can go to the same table, and V sub 1 should be equal to V no liquid but V gas. So from table A5 we know V1 will be equal to V gas, and again I don't know if you can read on the table, that's equal to 0.46242. 0.46242, and the unit should be cubic meters per kilogram. Okay, so something important from the figure. This is a closed system, a rigid container. It's not a piston cylinder. So that means that the volume is not going to change. So you can say right away V2 will be equal to V1, and this will be equal to 0.46242. Okay, V1 equals V2. So that's also important, because what is that telling us is that the process will be going through this line of constant volume. So we go from this line of 143.61 to this line of over here of 400, and this will be state 2. So 1 saturated vapor to state 2. Okay, so this should be like steps 0 and 1 on the procedure. Next thing we need to do is, what is the main equation that we know? Is the first principle of thermodynamics, which is Q minus work equal change in energy. If we neglect kinetic and potential energy, that means that Q minus work will just be equal to the change in internal energy. Okay, and what else do we know? By definition, the work done by pressure is PdV, and since the volume is constant, dV will be 0, so that means that the work over here will be 0, so that at the end we have that the change in heat will be equal to M U2 minus U1, or since they ask us to find this kilojoules per kilogram, will be equal to Q over M equal to U2 minus U1. Okay, so basically what I need to find is U2 and U1. So probably we can find U1 from table A5 as well, but let me just go to the next page. Okay, so let's say that we first going to find U1. So what do we know about U1? You always need to go to the figure. U1 is saturated vapor, at P1 equal 400 kilopascals, okay, on the line of 143.61 degrees Celsius. And we got that information from the table A5. So let's go again to table A5. At P equals 400 kilopascals, which is the same as for bar, what do we know? We know that U, the initial energy, will be at the U at the saturation. So this point over here, this is UG, this will be UF. So UG is this point over here. So we know U1 will be equal to UG, and that is equal to table A5, 400 UG, hard to read, let's see, but it's 2000. So at 400, maybe if I take the light off will help. Let's see if it's easier. No. Anyway, go to table A5 and you find out that at 400, UG is equal to 2,553.1 kilojoules per kilogram. Okay, now we need to find U2. So what do we know about U2? U2 we know will be on the superheated region, or will be a gas. So we need to find the table. So we know that it's superheated. Or gas tables. We know that T2 is 400 degrees Celsius. And again, the trick over here is that you always need to know two different properties. Here we know the pressure. Here where the pressure was enough, but generally you always need to know two things. So here we know the pressure, and what else do we know? Because this was a fixed or closed system, we know that V2 was equal to V1. So you can say V2 is equal to 0.46242. Okay, we could go and find the pressure, but this should help us to do the problem anyway. So let's go here to the table for superheated, which will be table A5. So this one is for pressure, that one is not going to help. Table A5. Okay, let's go to table A6. So we go to table A6 and we look for the different temperatures. You look at 400, you start looking at the V's. Again, really hard to show that. Let's see if I can approach it. Okay, basically you look here, the temperature will be 400, and try to look here the first column, which is the V's. I know it's not clear on the video. And you start looking, here is 31. Okay, so we start going down. So we'll try to find something that will be close to 0.46242. So if you go, you will actually find out that, so go to the book and please get table A6, which is page 892, and do this with me. So I'm looking for the V's, and it looks like it's going to be okay at P equals 0.6 megapascals. We have that at T equal 400, V is equal to 0.51374, and U equal to 2962.5. Okay, but we're looking for the 0.46. At P equal 0.8 megapascals, we have V is equal to, at 400, 0.38429. And U would be equal to 2960.2. Okay, so what we need to do now is interpolate. I have a special video just for interpolation, but here I'm just going to try to redo it very quick. So basically we need to find what would be the U value for V equal to 0.46254. So if I do a figure, what we're trying to find is always would be on the y-axis, so put U over here, and what we know here is the V. And we do a linear interpolation, so we're always going to have some type of straight line. Okay, what I need to find out is what do we put on each one. So let's see. It doesn't matter from where you start, but let's go from lower to higher. So which one is the lower will be, so it's V over here. Let's say this will be V sub A, 0.38429. And at that value, U sub A is 2960.2. At point B over here, if you want to call this one A, B, we have V sub B equal to 0.51374, and U sub B over here is 2962.5. Okay, so in order to interpolate, again, we did that, so we're trying to interpolate over here the value U2 at the value V equal to 0.46242. Alright, so what we do over here is U sub 2 will be equal to what? If we start from this point, 2960.2 plus what? The slope of this curve, that will be how much it goes up for the increment, will be 2962.5 minus 2960.2. So divided by 0.51374 minus 0.38429 times this increment here, which will be 0.46242 minus 0.38429. And if you do this calculation, you get 2961.59 kilojoules per kilogram. So finally, the change in heat equal to U2 minus U1 will be equal to 2,961.59 minus 2,553.1, which gives 408.5 approximately. Okay, and this will be the final answer. So I'm going to attach the PDF file to this video in order that you can see the files, the tables as well. Thank you for your time.